Natural physics is a concept I developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as my astrophysics research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Imagine it's 37,000 years ago. A Cro-Magnon or Neanderthal is out in the middle of a savanna. 400 yards distant looms a saber-toothed tiger. 50 yards in the other direction stands a tree. As our primeval ancestor instinctively compares the distance between himself, the saber-toothed tiger, and the tree, and the time that he thinks it'll take for that tiger to get to him, as opposed to him getting to that tree, he's doing a rate comparison of distance with respect to time. Velocity. He's doing physics,
but not from a blackboard or out of a textbook. He's doing physics by observing the world around him to survive.
He's doing logic too.
He's doing natural physics.
Seeing birds.
That's right.
There's birds. There's something dead there.
That's
Maybe I can get some bones. I can get some marrow.
That's
Our primeval ancestor instinctively calculated the velocity of the saber-toothed tiger on an everyday scale of meters per second. The Fermi Gamma Ray Space Telescope uses advanced computers to calculate the velocity of cosmic rays on a relativistic scale of thousands of kilometers per second. And the ancient Sumerians calculated the velocity of Nibiru on a planetary scale of tens of kilometers per second. Whether here in the present, in the far future, or the distant past, natural physics surrounds us, as does our amazing world of nature.
We don't want our story to end so quickly. And also, if our primeval ancestor does not make it to that tree, then we won't be around. So he makes it to the tree and is able to climb it before the saber-toothed tiger can get to him. He did natural physics in having instinctively determined that the velocity with which he could run to the tree would be enough to get him there before the saber-toothed tiger could get to him with the velocity that it would be running at. As he sits at the top of the life-saving tree, watching the tiger as it paces back and forth around the bottom of the tree, looking hungrily up at him, he begins to ponder. What first comes to his mind is that he wonders what would have happened if he would not have been able to make it to the tree. He wonders if he would have been able to go toe to toe with the tiger and fight it off barehanded. He thinks about how big he is compared to the saber-tooth, and he thinks about how strong he is compared to it. He is again instinctively doing a rate comparison, a pound-for-pound comparison of his muscle mass compared to the tiger's muscle mass. He observes that both he and the saber-tooth have about the same size. They take up about the same amount of space or volume. However, he also observes that the saber-tooth's muscle mass is much greater than his. He instinctively and correctly concludes that the tiger's density, which is the tiger's mass with respect to its size, is greater than his density. Again, he has done natural physics to survive, natural physics that helped him determine that it would not be wise to try to take on the saber-toothed tiger single-handedly and without any weapons or fire. Just when he thinks things couldn't get any worse, as he perches trapped high up in the tree, clouds begin to gather overhead, and there's the rumble of thunder in the distance. All of a sudden, there's a flash of lightning. Our ancestor is instinctively afraid of lightning, maybe even more so than he is of the saber-tooth. As he looks down again at the circling tiger, much to his surprise, he discovers that it is gone. And then he thinks about what is it that lightning has that he doesn't, which scared the saber-tooth away. As he jumps out of the tree and runs for home, he begins to think. Lightning is bright. He knows that the brightness of fire keeps saber-tooths at bay. He also instinctively realizes that he himself does not give off such brightness. He then knows that he doesn't have this property that lightning has, which is luminosity, the ability to shine, to give off light.
I like that.
Next, he thinks about how he has seen lightning strike trees and create fire. Fire has heat. He does not understand what temperature is, but he knows that fire burns and that saber-tooths are also afraid of it. He realizes that he does not have this property of fires either, which is the ability to give off enough heat to burn. Next, he thinks about how he has seen lightning strike and kill animals instantly. He does not understand what electrical current is, but once again, he realizes that here is another property of lightnings that he doesn't have, which is the ability to kill a saber-toothed tiger on the spot with one touch. Through observing the world around them, our primeval ancestors made instinctive deductions. To survive, they had to be able to make comparisons between objects that they knew about based upon their observations and their experiences. This scenario presented a storyline in which a primitive human could have instinctively created the concepts and use of the 7 basic physical quantities of physics: length, time, mass, volume, luminosity, temperature, and electric current, along with the 2 derived physics quantities of velocity and density. Other scenarios will present in like manner ways in which the other laws of physics and the mathematics along with that could have come about through observing nature.
Physics is the oldest of sciences. Even older than astronomy and mathematics, physics has been with us since the dawn of humankind. Before our primeval ancestors began to gaze up in wonderment at the stars in the night sky, they were busy looking around at their surroundings to survive. Before they began to squint up at the blazing sun in amazement, they sought to possess its life-giving warmth through fire. Physics is older than biology and chemistry. Before our primeval ancestors wanted to know what the plants, the animals, the air, the water were made out of, they wanted to know their own physical capabilities. Before they learned to count each other, they learned the laws of nature. But these are not the survival of the fittest jungle laws, no. These laws our primeval ancestors learned instinctively by observing the world around them. These laws would aid them in being successful on the hunt instead of becoming the hunted. These are the laws of physics. Yes, eventually they made their way into our textbooks and upon our blackboards, but they did not originate from either. These laws came from our primeval ancestors observing the world around them in order to survive. These are the laws that come from observing nature. These are the laws of natural physics.
Just to be around me.
What made the Hulk the Hulk? Gamma rays. Gamma rays are the most powerful form of energy known to exist in nature. More powerful than microwaves and X-rays, gamma rays come from cosmic rays. Cosmic rays were first discovered in the 1920s, and no one knows where cosmic rays come from.
Gamma rays are very highly energetic photons and are at the extreme end of the electromagnetic spectrum. The visible range in which we see is a small part of this spectrum. Just as a group of 6 runners will break apart when running from the beach into the ocean, a beam of light separates into the 6 primary colors of red, orange, yellow, green, blue, and violet because these colors travel at different velocities when going from one medium into another. Cosmic rays are high-energy protons, ions, and electrons that astrophysicists believe are produced when a star explodes into a supernova. As the shock wave from the explosion expands out into space, it encounters protons, ions, and electrons. Its magnetic field pushes them up to very high speeds, and they gain energy by repeatedly crossing the shock. The process, called diffusive shock acceleration, or DSA, is thought to be facilitated by scattering off magnetic turbulences downstream and irregularities upstream. Charged particles change trajectories when they encounter a magnetic field, making it impossible to directly determine where cosmic rays come from. The source of gamma rays are traceable because photons have no charge and are unaffected by a magnetic field. Cosmic rays can reach energies up to 10 to the 21st electron volts, and below 10 to the 15th electron volts are thought to be of galactic origin. The most promising sources of galactic cosmic rays are supernova remnants, or SNRs. They are not only energetically favorable, but also provide a mechanism to accelerate particles to very high energies. An important window of observations in the range from 100 mega to 300 giga electron volts has been opened with the launch of the Fermi Observatory. Much of the gamma ray emission can be explained by Bremsstrahlung emission and inverse Compton scattering. However, the model cannot fit a distinct feature at giga electron volt energies, which can be accounted for by adding a pion component to the model, providing evidence for cosmic ray production. Despite all the findings that link SNRs with high-energy electrons, direct evidence for the acceleration of ions by these objects is still lacking. In order to find a signature for proton acceleration, studying the photon spectrum of the sources at gamma ray energies becomes fundamental. It is expected that a fraction of the high-energy emission would be caused by the decay of neutral pions produced through collisions of accelerated protons with cold ambient protons and ions. If the astrophysicists can prove that the accelerated protons are producing the gamma rays, then the mystery of cosmic rays will be solved.
Ancient physics keys to modern astrophysics locks. Many of today's unsolved mysteries in astrophysics were previously encountered during ancient times. In some cases, solutions were even known then that could be of help now to today's astrophysicists.
Astrophysicists have long suspected that a planet once orbited around the Sun where the asteroid belt is, between the orbits of Mars and Jupiter. But when all the masses of the largest asteroids, such as Itokawa, Ida, Gaspra, and Eidos, along with the other asteroids, are added up, the sum is not enough to make up a planet, only perhaps a large moon. If the asteroids are the result of a planet breaking up and the pieces continuing to orbit around the sun, making up the asteroid belt, then where is the missing mass? The answer was provided 6,000 years ago by the Sumerians, who lived in the region of Mesopotamia and are considered by archaeologists to be the first civilization. They predated and influenced other ancient cultures such as the Egyptians and Babylonians. According to the Sumerians, a planet called Nibiru with an elliptical period of 3,600 years orbits around the sun as part of our solar system, and a gigantic planet called Tiamat did once exist between the orbits of Mars and Jupiter. On one trip back into the solar system, Nibiru's gravitational field pulled Pluto away from its original orbit as a moon around Saturn, and then pushed Pluto into its present orbit around the Sun. Saturn was able to hold on to its other moons, such as Titan and Mimas, Enceladus, Pan, and Rhea. Pluto has always been different from the other planets in the solar system. Its size is more suitable to being a moon rather than a planet. In fact, our own moon is larger than Pluto. As Pluto orbits the sun, it has a reverse spin compared to the other planets, and its orbit lies 17 degrees outside the elliptical plane in which lie the orbits of the other planets. And yet, on another journey into our solar system, Tiamat's powerful gravitational field captures the largest moon of Nibiru. The other moons of Nibiru change trajectories from the close encounter and become comets, each with its own trajectory. These mysterious members of our solar system visit us at regular intervals. And finally, upon re-entering the solar system, Nibiru collides with Tiamat. Tiamat breaks into half. One half becomes the Earth, and from the collision, the moon previously captured from Nibiru pulls the Earth into its current orbit around the sun. The other half of Tiamat broke up and became the asteroid belt. Here, we have a 6,000-year-old solution to 4 of today's unsolved problems in astrophysics. The missing mass riddle of the asteroid belt, to why Pluto is now no longer considered a planet, to where comets come from, and even to the very origin of our own Earth and Moon. At the very least, these ancient solutions can serve as a starting point to help today's astrophysicists, and at the greatest, these ancient solutions can actually be the solutions that astrophysicists have been searching for. We will examine in detail these and other ancient solutions and determine their plausibility based upon our current understanding of physics.
Have you ever used the expression aha when you finally figure something out? The pyramid builders of the ancient civilization of Egypt, located on the continent of Africa, used algebraic equations written in hieroglyphics to construct their pyramids. In algebra, the goal is to solve for the unknown variable, x, the unknown. The ancient Egyptian word for their unknown variable in their algebraic equations was, get this, aha.